Okay, one more modelling paper, making cones. This is quite a recent one from June 2019, paper 6.2. Remember, they don't give you a formula sheet in the paper 6, so that is why they've given you some formulas up front. So it tells you the circumference of a circle, c equals 2 pi r, the volume of a cone with radius r, height h, v equals 1/3 pi r squared times h. The curved surface area A of a cone of radius r with sloping edge L, A equals pi rl. So they're just written in the formula book that you would get in paper 2 or 4. This task looks at modelling the volume of a cone which is made from a circular disc. In this part, lengths are given in centimetres and angles in degrees. Raj makes a cone from a circular disc of radius 18, so 18 centimetres. You can see the disc here. He cuts out part of the circular disc, leaving the shaded sector with angle x, sector angle x. The cone that he makes has base radius r and height h. So what he does, he gets a circle here, he cuts an angle out, makes a sector, doesn't use this bit, he does use this, and he folds it around, and then he makes a cone out of it. The cone that he makes has base radius r here and height h. Show that the arc length of the shaded sector is x pi over 10. Right, so if we just deal with the shaded bit, you know that circumference of a full circle is 2 pi r. So the circumference of a sector, well, it's the fraction of a circle that the sector is times 2 pi r. So arc length of any sector is x over 360, this is x being measured in degrees, times the actual circumference formula, so times 2 pi r, right? So that's what we're going to use. So in our case, arc length, well, it's x over 360 times 2 times pi times r is given at 18. Okay, well, if you look at that, 2 times 18 is 36. So you've got 36 on the top and 360 on the bottom. So 36 here over 360 can be written as 1 and 10. And that's where you get your x pi over 10. X pi over 10. The arc length forms the circumference of the base of the cone. So when we roll this thing up, we imagine this dashed bit's not there, so we've taken this white bit away. We're just dealing with the shaded section, and this part here, that's going to meet this bit, and it folds around to form a complete cup, that sort of shape, which looks like this. Now that has a circumference here. Now the whole circumference of the base of the cone has got to be equal to the arc length, because that it folds around and then it meets. Right, so that's your formula. So our arc length of sector, must equal circumference of cone. Circumference of cone. So that's the formula. Then we just need to write those down mathematically. Well, we know arc length of sector of this particular sector is x pi over 10. So x pi over 10 equals, well, the circumference of a cone. It's just going to be the circumference of that circular bottom, which is 2 pi r, and the radius is r, so equals 2 pi r. Then we just need to make r the subject. So r is going to equal, well, we've just got to get rid of this 2 pi, so we divide by 2 pi. So it's x pi over 2 pi times the 10 that was already there. Pi divided by pi is just 1 and 1. So you end up with x on the top and 2 times 10 on the bottom, which is 20. So r equals x over 20. Okay. Show that h equals the square root of 324 minus x squared over 400. So we need to find an expression for h. If we go back here, you can see that h is the height of the cone, and we've got this triangle here. So you can see, just using your Pythagoras theorem, it's a right angled triangle. You've got the two short sides, so a squared plus b squared equals c squared, where a and b are the two short sides. You can write a and b down any way you like, so I'm just going to put the unknown, the wanted one, first. So h squared plus r squared must equal 18 squared. I can just draw the triangle as well. So this is the triangle. We've got an h, an r and an 18, so that means h squared plus r squared equals 18 squared. And then we've just, if we look at what we're aiming at, there's no r in this, so we need to use what we've got already. We know that r can be written as x over 20, so I'm going to replace that. So h squared plus x over 20 squared equals 18 squared. So if we want to solve that for h, well, get rid of the x plus 20 squared. So h squared must equal 18 squared minus x over 20 squared, and I'm now going to tidy that up. So 18 squared, if you're not sure, just go to your calculator. 18 squared is 324. So h squared equals 324 minus, well, x over 20 squared is x squared over 20 squared. Now 20 squared is 2 times 2 times 10 times 10. It's 400, but if you're not sure, just use the calculator. So this is h squared equals 324 minus x squared over 400. So we're nearly there, and we now just need to solve for h, so we square root. So h must equal the square root of all of that. 324 minus x squared over 400. D1. Show that a model for the volume V of the cone is V equals 0.026 x squared times the square root of 324 minus x squared over 400. So we need to find an expression for the volume of a cone. So if we go back to our first page, you should remember it anyway, but it is given to you. Volume of a cone of radius r, height h, so V equals 1/3 pi r squared h. So let's write that down. V equals 1/3 pi r squared h, right? So now we actually have an expression. Look at this again, there's only x's in this. So we have r in terms of x, and we have h in terms of x. So hopefully that should get us to this expression here. Okay, remember r is x over 20, so that equals 1/3 times pi times x over 20 squared, which actually I could have just written that as x squared over 400. Probably should have done with the space, but never mind. Times h, well, we've just said h is the square root of 324 minus x squared over 400, right? So if you look at what we're aiming at, this bit's fine. I don't need to do anything with that. I just need to sort this out really. So equals 1/3 times pi times x squared over 400. So over 400 times the square root of 324 minus x squared over 400. So really, I just want to, you can see here, I've got an x squared and an x squared, and then I just have a number. So I'm hoping that 1/3 times pi divided by 400 is this 0.0026. So 1/3 times pi over 400. Let's see what that equals. 1/3 times pi. I'm just going to do that and divide by 400. And that's giving me, annoyingly, it's given the answer in standard form. So that's telling me it equals 2.61799 times 10. That little e here, that means times 10 to the power minus 3. So if you've got one of the old calculators, it's not a bad thing to see this actually, because this could really throw you in an exam. So I just need to divide this number by 10 3 times, and if the decimal point's already there, it's going to be 0, 0, 0. So equals 0.00. There's your 3 zeros, and then you've got your 2 6. So the volume must equal 0.0026 x squared, and I'm not going to have room, square root of 324 minus x squared over 400, just about. It's not nice, but they don't really give you a lot of room. I do think it's very strange that. Use part 1. Remember, if it just says part 1, it means part 1 of the same question, so it's this D1 here. Use part 1 to find the volume of the cone if Raj uses a semicircle of radius 18. So this keyword is semicircle. So if we go back to what Raj is actually doing, he's taking sectors with angle x, right? So basically it's saying, what if this sector is a semicircle? It's a special kind of sector. Well, if this was a semicircle, x would be 180 degrees. A semicircle means half a circle, right? So semicircle means x, which is the angle, equals 180. Okay, so now all we need to do is just plug 180 into here and here. So that would mean V equals 0.0026 times 180 squared times the square root of 324 minus 180 squared again over 400. Now, if this was me, I would be encouraging you, and I think you should be encouraged, to use your last answer. As in, when I'm plugging in this 0.0026, I think you should be plugging in this number here on a calculator, this 2.617993 times 10 to the minus 3, as in the most accuracy as possible. But because we've been told to use this model, we actually should just use this 0.0026, so use the prescribed model. And actually the mark scheme, if we do use this whole number, is outside of an acceptable range. So I think because it actually specifically says use part 1 and the model was given, then you do really need to use this model and not the greater accuracy version. I do think it's a bit unfair, but that's the way it is. So I'm going to type it in exactly as it looks like this. So 0.0026 times 180 squared times the square root of 324 minus 180 squared over 400. Okay, so that gives me 1313.17164. So that means I'll give it to 3 significant figures. So equals 1, 3. Well, you remember, find the third significant figure. Every figure is significant. So 1, 2, 3. Look next door. The 3 will not change the 1, so it's going to be 1, 3, 1, and then we need a placeholder 0. 1, 3, 1, 0. And if you want units, well, it told us at the beginning that everything, all lengths are in centimeters. So this is a volume, so it must be cm cubed. sketch the graph of the model for x between 0 and 360. Okay, so it's given us the x min, x max. It's given us a y min of 0. It hasn't given us a y max, so we'll have to adjust the window to get that. But we do know that, we know that when x is 180, we get up to 1310. So our y max has got to be at least 1310. It's a good starting point. The model is this here, so we need to put this in. So now we're going to investigate how the volume changes with changing sector angle. So menu graph, 0.0026 times x squared times the square root of, and if you've got one of the older calculators like me, you need to use a bracket. Just make sure you're taking the square root of everything and not just one thing. So that would be 324 minus, and also if you've got one of the older calculators, the fraction button doesn't work particularly well when you're actually typing into a graph function. So I'm just going to put x squared over x squared divided by 400. X squared divided by 400. Make sure you close the brackets off properly. Okay, if you've got a decent calculator, a bit of a newer calculator, you won't need to worry about this anyway. So there we go. And then we have a look at it. And we're looking at the wrong bit of the model. So we need to set the view window. We definitely want x min to be 0 and x max to be 360. Remember, we're trying to draw it on here, 360. And y min I definitely want to be 0, as you can see here. And remember what I just said, we know that we need to go up to at least 1310, so maybe I'm going to go up to 1500, have a look at that. 1500. And if we haven't got all the graph in, we'll just come back and change the window. So it doesn't look bad, but you can see we're missing a bit off the top. So we're going to go back in, view window, and I'm going to change that to 2000. Have a look at that. And I still can't quite get the top in, so I'm going to go to 2500. And hopefully then we'll be able to see the whole graph. If you're ever going off the top or off the bottom, you do need to look at your view window. Okay, so that's much better. Now we can see this is, as x gets bigger and bigger and bigger, you can see the volume is increasing, and then we get to a point where it drops rapidly. Right? So now we can draw the graph. Remember, for communication, we should say where this top bit was, and if you're not sure, just look at your view window. That's 2500. So this at the top is 2500. And then to draw that, well, I'm going to go quite near the top of the screen and towards the right, so probably somewhere around here. And then I want to sort of steepish curve up to there. And then it just sort of winds down to somewhere around here. So maybe something like that. Probably a little bit more kinky in there than it needs to be. But if it's basically doing the right thing, I think that would be all right. So mark scheme wise, if you've got any sketch with a single maximum, that's my single maximum, that needs to be somewhere around the correct area. And it needs to roughly look like that. So I think this is probably a little bit, does this a bit too much, but I don't think it's enough to lose the marks. But hopefully you can draw it better than I can. Right, for the cone with maximum volume, find the angle x, the maximum volume v, and the curved surface area. So maximum volume, we're interested in this point, and I always think it's good communication to just write that down and show the examiner that you know what you're doing. So to find a maximum, Shift G solve, we're looking for a max, and that says x is 293.9387 or 0.939. 293.939 we'll call it, and the y value is 2334.527. Okay, right, so we want to find the angle. Remember, x is the angle, so 293.939, we'll just call it 294. Okay, the maximum volume V, or this is V on the y-axis, so that number is 2334.4. We'll call it three significant figures. 1, 2, 3. We'll call it 2330. But with a question like this, I don't think you would. I don't think you'd be punished for doing something else. But I think three significant figures, if you're not sure, generally works very nicely. Now we need to find the curved surface area. That's a little bit more tricky. And we're going to go back to the formulas that we were given at the start. And it says curved surface area A of a cone of radius r, sloping length, sloping edge L, A equals pi RL. So let's write that down. Pi RL. Do we have L, right? So when it says L, well, L is the sloping edge, and actually this is L here. So L was 18. It didn't, when X changes, L actually doesn't change. It's just the radius of the sector and the sloping edge of the cone. So L is 18. R is X over 20. That could be useful. So R equals X over 20. L equals 18. And we know for them, the cone with maximum volume, we've got an X. Well, it's this 294. So that means A equals pi times R. And now I am going to use the greatest deal of accuracy, or certainly more than three significant figures. So pi times R, which is going to be 293.939x over 20 times 18. Okay, so let's have a look at that. Back to the main bit, the calculator. Pi times 293.939 over 20 times 18. And that gives us an answer of 831.0929, so on. So I'm going to put that in as 831. Curved surface area, it's an area, all lengths are in centimetres, so that can be centimetres squared. Right, number 8. Raj decides he can make 2 cones from his circular disc. So what he's going to do, he gets his angle X, and he does in a normal way, so cuts at an angle, cuts along here, and he folds it, but then with the material that was left over, he folds that around to make a different cone. So this one's going to be sort of quite a high, very thin cone, but it still will be a cone nonetheless. So one comes from the sector with sector angle X, so that's the one we've already looked at. The other comes from the remaining sector, this one, with sector angle Y. So you can see the angle Y and X. And it says, write down a formula for Y in terms of X. So that's quite friendly. You can see X and Y, they're around a circle. You know the angles around a point add up to 360. So X plus Y equals 360. Very simple angle. We probably learned it in primary school. So that must mean Y equals 360 minus X. Okay, very friendly question. The total volume of the 2 cones is V equals 0.026x squared times the square root of 324 minus x squared over 400. So that's the bit we've already looked at. That's the volume of the shaded cone. So vol of shaded, plus, and then we've got another bit with y's, so 0.0026 y squared times the square root of 324 minus y squared over 4. So it's the same formula but with y, so this is vol of unshaded. Unshaded. Question is, use your answer to part A to write down in terms of x the model for the total volume of the two cones. So it's given us one line, it doesn't expect us to do massive amounts of algebra. So all we need to do is replace these y's, and it tells us use your answer in part A. Well, this is our answer in part A, 360 minus x. So all I'm going to do, I'm going to copy this model down, and wherever I see a y, I'm going to write brackets 360 minus x, and I'm certainly not going to expand it, because where would I even do that anyway? So v equals 0.0026 x squared 324 minus x squared over 400 plus 0.0026. So it's y squared. Y is 360 minus x. 360 minus x squared times the square root of 324 minus, so y squared, again it's this 360 minus x squared over 400. So even just writing that model, I barely fitted it on. Sketch the graph of this model. So this is going to take a while to plug it in, but actually if we go back to our graph, it's not that bad because we've already got the x function in, so all of this first bit is already in, so we just need to go and put the rest in. So start from here, then we need to add 0.0026 to 360 minus x squared, 360 minus x, close the bracket, squared, times the square root of, remember make sure you get your brackets right here, square root of 324 minus, so my calculator is not very good, so I'm going to use a bracket and a divide, 360 minus x squared, I might need two brackets there, so 360 minus x squared over 400. So I'm going to need a bracket there. I need another bracket there because I'm taking all of that away. And I'm going to need another bracket because of the square root bit. And then hopefully that works. The view window, it's actually told us more information. It's given us a y min and a y max, so we need to make sure we put that in. We'll keep the x's to 360. You can't go beyond 360. So let's go shift V window. We'll keep the x's the same. Y min we're going to make it 2500 and y max 2700, just like that. And then we've got this interesting little, almost a little M, so you've got this double humpy thing. Right, so it looks like this looks fairly central. It kind of goes down here. It comes down somewhere around here, and it sort of goes up to a point a bit higher. These look level, so somewhere maybe around here, and then we just kind of draw a nice sort of flowing M. I'll try and do a better job than my last one. Okay, so something like that. Again, it's not neat, and I'm sure a lot of people will do this a lot better than me, but I think it's just about good enough for the marks. I'm not entirely sure if this bit's as nice as I would like it to be, so maybe I'll just alter that section a little bit, so it needs to sort of come around a bit smoother. That's a little bit better. Okay, so that's the graph. find the two angles that give the maximum total volume for these two cones. Remember, angle is x. I might just write that I went up to 360 again, just to show some communication. So I'm looking for maximums. Shift G, solve max. So the first one is 116.644. I will put these in again. So I'm just going to, because I'm going to write two of them, I think I will round this time. So 116.6. And the volume is 2644.8. The one over here, if I just move over here, 243.35, so 243.4, and 264, so it should be the same number. It's told us that there's one maximum total volumes and two angles that give it 2644.8 again. So the answers, I'm tempted, because it's not that close to it, I'm tempted to put a decimal place. I think if you put 117 or 116.6, it would be okay. But I'm going to put 116.6 and 243.4. But if you just put the whole numbers, that would get you the full mark, so I have confirmed that. Instead of the circular disc of radius 18, Raj now uses a disc of radius 36 to make one cone with maximum volume. We need to find the volume of this cone and the angle that gives this volume. Right, so I've got a bit of space. I'm just thinking how you would tackle this in an exam. I'm going to go back and build a new model, plot the graph, try and find the maximum point. So we are going to go back to the start. So if you have a look at the beginning, remember how it started. So we had this sector of 18, so basically this is now 36, right? So we built a model for cone volume, and it came from, we got expressions for arc length, for radius in terms of x, and then we had height in terms of x, and then we used those to find the volume model, right? I'm going to do all of that from scratch, and hopefully it won't take too long. So if we start from the beginning, so remember, show the arc length of the shaded sector is pi x by 10, or x pi by 10. So what we're going to do, remember, arc length equaled x over 360 times 2 times pi times r. So that means L equals x over 360 times 2 times pi times r, and in this case r is now r is 36, it was 18, 36, right? So that means you've got 36 over 360, we'll cancel those to 1 over 10. Then you've got 2 over 10, which can become 1 over 5. So that means L equals pi x over 5, or x pi over 5. Okay, so that's the first bit. Then the next thing was to get an expression for the radius in terms of x. So remember, arc length of sector, we just worked out, L equals circumference of the cone. So the expression for L that we just got, which was x pi over 5, equals 2 pi r. Solve for r. X pi over 5 equals 2 pi r. So r must equal x pi over 5 times 2 pi, just divide by 2 pi. Pi, cancel, 1, 1, you've got x over 10. So r equals x over 10. Remember, it was x over 20 before, so it is a bit different. Okay, then the next bit was this expression for h, right? So we are showing that h equals square root of 324 minus x squared over 400. Remember, we had this triangle here, so it was r, h, and 18. Well, the 18 is going to be 36, so we're going to have h squared plus r squared equals 36 squared. So h squared plus r squared equals 36 squared. So that means that h squared plus x over 10 squared, which I'm going to write with x squared over 100. 10 squared is 100. Equals with 36 squared. Go to the calculator for that one. 36 squared gives us 1296. So remember, we're looking for a model for h, which means we're going to subtract the x squared term and square root it. H equals 1296 minus x squared over 100 and the square root of all of that, right? Okay, where did we go next with that? The next place we went with all of this was to get a volume model. Now this has a decimal. I'll probably leave the decimal out, to be honest. So the volume model, volume of a cone, remember it said at the front, volume equals 1/3 times pi times r squared times h, right? So V equals 1/3 times pi times r squared times h. So V equals 1/3 times pi times r squared, x over 10, or x squared over 100, sorry, times h is this square root 1296 minus x squared over 100. Like that's the volume model. Now we could, let's make sure you can see it. So that's the volume model. Now what we could do is write that as a decimal, as in multiply all of this together, or you could just whack it in like that. I'm tempted just to put it in like that. So I'm going to go back to the graph and I'm going to type in 1/3. Now my calculator is no good, so I'm going to put in brackets 1 over 3, or 1 divided by 3. But if you've got a decent calculator, you can just put 1/3 times pi times x squared over 100. So remember, my calculator is no good, so it would say x squared divided by 100 times the square root of, in brackets, 1296 minus, and then I've got x squared over 100, so it's going to say x squared divided by 100. Close that bracket off, close the other bracket off, and I think that should be good enough for the model. Now if we draw it, I can see I'm looking at the wrong part, so I'm going to go back to the view window. Remember, for our graph that we had before, we had a minimum of 0, maximum of 360. We've got that. It's the y's that are the issue. We've got these limits from when we drew the 2 cone thing. So I'm going to take y min back down to 0. I might keep y max the same and have a look. And I'm still going off the screen. It does make sense that we can get a bigger volume out with, because we've got more material to build with. So let's keep going up. So maybe, I don't know, 4,000. What about that? Still off the screen. View window. Let's go to 10,000. Still off the screen. Let's go to 20,000. And finally, we get a curve that looks like it makes sense, and thankfully it does look the same. So if we're going back to what we want to do, I'm just going to draw a little sketch, show some communication. That's not very good, but never mind. I want to know the volume of the cone. That's the biggest one, so Shift G solve, looking for the maximum. Looks like the maximum volume is 18805. The x value is 293, so we've got the same angle. And the y value is 18805. Okay, so the volume 18, I might round that to 3 significant figures, so 18800 centimeters cubed, and the angle is the same. So that means that potentially we could have probably done this in a more efficient way, not necessarily an easier way. I think this is the way that most people would probably do in the pressure of an exam if you have time. Sometimes it's quicker to just go back and use the processes that got you there rather than actually make a connection. Anyway, the angle is still 294 degrees, so that probably means we could have done something a bit quicker, but this has still got us to the same place.